Introduce you.
You go.
So, there's a dangerous place in the Salisbury Plain where they do things. They shoot at each other, and you're meant
Only with blanks.
You're meant to be controlling all of that. Anyway, we're very happy to have Ronni here. And from what was just said, your policy and decision making may be part of what you have to say.
I work for DSTL. There's a bit in this talk about who we are and what we do. I'm going to give you a little bit of background. So we're going to start all the way at the beginning, bit of a change of pace. Then I'll tell you a bit about DSTL. Then I'm going to give you a motivating example. Then I'm actually going to do a little bit of maths because I am at heart a statistician, just a very, very applied one. Then I'm going to talk about communication, and then I'm going to give you a bit of a think piece on how quick we need to do things. So, uncertainty. We're kind of all, I hope, vaguely aware of uncertainty. I'm teaching you to suck eggs here. We have definitions, there are different types. That's just a very, very brief split. I could split that lots and lots of different ways. Tony's got a very good definition. I think there are 6 types of uncertainties in your definition. Didn't fit on my slide though. But there's lots of different types of uncertainty. But why are we doing this? Why are we here? Why does it matter? Why can't I just give an answer? And my argument is that the reason that we can't do that is because in order to make a decision, we have to have some appreciation of the risk that we are taking when we make that decision. Now, just like there are different definitions and different types of uncertainty, unfortunately, it's the same with risk. Different types of definitions of risk. I generally go with the second one because that's what I work with. So I tend to define risk as the probability that something might happen multiplied by the effect of that happening. So if something's very, very unlikely to happen but is going to have an absolutely massive effect, then I might want to worry about it. Which is why I tend to work on the problems that I do, because they're very, very low probability, but they're very, very, very high impact. The problem is that actually everyone perceives risk differently. So my perception of how risky something is going to be different to every one of your perceptions of how risky something is, because it's not only based on the mathematical uncertainty, it's also based on your experience, how you make decisions, how you think about things. So in general, nobody thinks twice about getting in their car and driving to the shops. A lot of people think twice about getting on a plane. That's more scary. Statistically, that's rubbish. You're far less likely to die in a plane than you are in the car. That's because my individual assessment is changed by how often I do. I get in my car every day. I haven't, generally don't crash. It's all fine. I might not do that with an aeroplane. So a human's ability to assess risk depends not just on the rarefied mathematical calculation of the uncertainty, but also on their experience of what's happening. And when I give someone an assessment of uncertainty, I have to appreciate that they will take that uncertainty and they will morph that into their own risk assessment. How likely is it that something bad is going to happen given that? And worst case scenario, if I give them an uncertainty that they don't believe for whatever reason, they will ignore it completely and do what they want. That could be bad. So I have to give them uncertainty in a way that they understand and a way that they can do something with. Which brings us to communication. It has to be timely, it has to be effective, and it has to be audience specific. Now, we've had some wonderful talks, but I'm sure none of us would give that to a decision maker, because the decision maker is going to take one look at a lot of the talks and go, don't know. So it's always audience specific. And how we present uncertainty is very, very specifically audience specific, because it's such a hard concept to get our head around. I think a lot, and I am as guilty as everyone else of us, kind of, we play with it all the time, we think about it all the time. We don't realise that this is a really hard concept to get our head around. The amount of times I have been told, stop doing that, give me an answer. I would be a very rich woman if I had £1 for every time someone said that. people just want an answer, right? They are busy, they are stressed. In my situations, they could be being shot at. If I'm like, well, you know, there's a probability distribution with support across the whole real line, they're really going to get quite cross with me and ignore every word I say. If I say, do you know what, I reckon that you'll be all right if you do that, based on some very sound appreciation of the uncertainty, then that's helping them. What I can't do is make the decision for them, because I don't have the skills to do that. I have the skills to determine what the probabilistic assessment of a risk is, but what I'm not doing is making the decision, because there are an awful lot of things that go into every decision, not just the uncertainty. What's going on at the time? What else is happening? What do I need to do next? What happened before? What's that guy over there doing? The mathematical community at the moment can do numerical modelling, we can do assessments, but what we can't do is a full appreciation of everything. So we have to enable the decision maker to do that themselves. There's some really good work on how we start to do this, and the best stuff that I've seen so far is some of the work looking at how you tell people the risks of having medical tests. So David Spiegelhalter did a little bit of that. He's come up with some ways. This is an example of looking at, well, what should I have this test or should I not, and what are the risks associated with that. There are other things along that line, and it's about talking to your audience and figuring out what they understand and what they don't. So, who am I and why am I bothered? I work for DSTL. We are the Defence Science and Technology Laboratory, and we aim to maximise the impact of the science, the stuff that you guys do, for the UK defence and security. So I take the mathematical stuff that you develop and try to apply it to solve specific problems. Therefore, the easier you make your explanations, the better and easier my job is. What do? Well, we provide advice, we provide support. There are operation analysts that will actually deploy to theatre with our troops. We manage the scientific programme. Interestingly, I think at the moment it's approximately half, maybe a bit more of our funding comes in and goes straight out the door to academia and industry. So we act as the technical interface between MOD and academia, for instance. So what we say is that anything that can be done in academia should be done in academia. So I will take your work and translate it, but if I think it's better done in academia, that's where it will be, and I'll be knocking on your door. We have lots of different capability areas. We actually have an entire capability sitting in analysis. Uncertainty, quantification, I know Tony doesn't like that term, but sits across every single one of those capabilities. I, in fact, sit here, despite the fact I'm a statistician, rather than here, and there are statisticians across the board. So what you do helps everything that we do. I'm going to motivate it though, the area I work in. I'm going to look at hazard assessment. So this is the real life nitty gritty, what it is I want to be doing. In an emergency involving a CB, chemical or biological release of a substance, we need a hazard assessment. So something's happened, what's the risk? Why do I need a hazard assessment? Well, do I need to get people out of the way? Do I need to treat them? Do I need to cordon off an area? Where do the police go? Where do they not go? Do I send in ambulances? All of these decisions have to be made, and they have to be made quickly. So to do that, I need to have a hazard assessment that tells the decision maker something about the areas that are affected. So in which area is it lethal? Where is there an incapacitating dose if we're talking about chem? If it's bio, where's there a probability of infection? What do I need to do to get across where the risk is so that they can make decisions about what they're going to do? Generally, our outputs look something like this. So that's a hazard area. Over an area, we've got kind of a red bit, that's bad, an orange bit, that's not quite as bad, a yellow bit, well, that's bad, but probably don't worry about that yet. You know, it's very simple, red, amber, green. Even charts like this cause confusion because there is a solid line about that red bit, which means that in a very instantaneous, something's happening, you know, this is a serious situation, what you have is a decision maker going, okay, I'm all right now, which, you know, that's amusing. But if you're really stressed and someone's drawn a line on a map and you're going, okay, right, well, I'll be over here then, you don't stop to think, actually, that's kind of a fuzzy line, and the uncertainty that's built that up means that it could be sort of on a nice, you don't stop to think about that, you just sort of move over here. So how I present that and how I calculate it is really important. So how do I get a hazard area? We use dispersion modelling. Dispersion modelling comes in lots and lots of different forms. We use a very simple Gaussian one because it needs to be fast. Lots of you will come across CFD. That's another way of doing dispersion modelling on a smaller and more accurate scale. You can have super fast sort of analytic ones. Lots and lots of ways of doing it. Interestingly, dispersion models, particularly the fast ones, aren't as accurate as you would assume from the output. So we're looking sort of factors of 2-ish for some of these dispersion models. Not all of them, some of them are better than others, but you know, the quick and dirty ones, factors of 2, about. CB hazard dispersers in the atmosphere, it's blown by the wind. If I want to run any of those models that we had on the previous slide, I need to know some stuff. I need some inputs. We've talked a lot about inputs. I need the source term. Where does it come from? Why is it released in the first place? Did it go bang? Is it a sprayer? How much was in it? How much of what was in it is actually causing a threat? What's the wind doing? Really need to know that. What's the terrain look like? How does it interact with the buildings? All of these are input parameters, and every single one of those is either uncertain or massively uncertain. So, I've got this kind of model, and I'm going to accept that my highly uncertain input parameters are kind of known. What I want to do is protect against it. Well, I'm going to might place some sensors then. So we've got some sensors that they could detect. Where should I put those? This is our first mathematical problem. Where do I put my sensors to maximise the chance that I will see one of these releases before it causes a problem, or in enough time for me to do something about the problem before it causes deaths, incapacitation, that kind of stuff. So what we do is a standard kind of mathematical approach. We run a Monte Carlo sample of a couple of thousand dispersion model runs, Monte Carloing over the meteorology, where it was released, how much it was, what kind of release it was. Already we've got a lot of parameters, we've got a lot of runs. We run those dispersion models forward, we get a nice output surface, and then we run an optimizer over it. And we optimize our sensors based on the output surface that we've generated from our dispersion model runs. We use a simulated annealing algorithm. We've tried lots. We are scientists. We do those kind of things. Simulated annealing seems to work best. But it's not easy because it's a real world problem, which means that two of the really key things we're interested in, probability of detection and warning time, for instance, are correlated. So I could get a really good warning time score by putting all my sensors really far away from my base, because then I'd see it and it would take ages to get to me, which would be great, apart from the fact that then they'd be really spread out and I'd miss most of them. So while the ones I saw I'd get a great warning time, I wouldn't see them all. If I stick them all in the middle of my base, then I've seen them all. Great, but I haven't got any warning time at all. That's not an easy thing to optimise. There's also areas that we might not want to put sensors. Roads, airport, runways, good examples of them. That's a hard edge though. Now I have to optimise with a hard edge. Anything with a hard edge in is hard to optimise. So these are all difficult. And interestingly, all of my optimisation is to get things like probability detection, warning time. But what I really want to do is rapidly optimise for casualties. I want to minimise the number of casualties that I receive from any particular release. That is the answer to the questions. Where do I put my sensor to minimise my casualty? All of this stuff is trying to get at that because it's too hard to get at, and I'll show you why it's too hard to get at easily a bit later. So next, I've kind of put my sensors out. Great, and my optimisation, actually it works relatively well, means I'm picked up, something's happening. So that's great. I've got a sensor going off. What does that tell me? Well, it tells me that there's a risk somewhere, but it doesn't tell me where it is. It doesn't tell me where it came from, and it importantly doesn't tell me where it's going. That's where we get to source term estimation. The point of source term estimation, it's an inverse problem, is it says, given my sensor reading, where was it? And the reason it says, where was it, is that it wants to say, therefore, where's my hazard? So, we've developed a Bayesian probabilistic method for figuring out where the hazard was in order to predict where the hazard came from, i.e. the source term, in order to predict the hazard. That's not necessarily easy either. You have to start with the fact that you don't know when there's going to be a release or if there's going to be a release, so you have to have a release, no release. We use that with a surrogate mass parameter, so we kind of say, well, if the mass is less than 0, that means there wasn't a release. So it's kind of a jury rig to get a probability of release. We also have to infer the metrology because we don't exactly know the metrology. Metrology is uncertain. We won't have an accurate method for the uncertainty on the metrology, so we have to estimate it. We then calculate a likelihood based on sensor reading. So what is the likelihood of a particular sensor reading given the mean and the variance out of my dispersion model? And we can calculate that using a sensor model. And we can use that to estimate the posterior distribution of a release, a source, a location. Unfortunately, that source term is at a minimum 15 input parameters, so it's multidimensional, and that's if you only take one particular metrology. So if you assume your metrology is constant over your domain. If you allow your metrology to vary in space and time, then the number of dimensions explodes, because for each one you have a mass and you have a location and you have a time. So this is a massively multidimensional problem. And you've got to infer it all from a set of small sensor models. Our other issue is that we need to estimate this. It's a Bayesian inference problem, so we're going to need a proposal distribution. Proposal distributions are great if you've got an idea of what it might be. If you don't, then you're a bit stuck. So we stumbled across differential evolution Markov chain, which allows your proposal distribution to fix itself to the problem. So it allows it to move, basically, and figure out where it should be proposing stuff through time, which means that in our case, as in we're getting more and more data through time, it will shrink the proposal distribution, but it will also importantly allow it to expand again without us specifying it. That works well for us. I haven't seen it used anywhere else particularly. That could be because there's something massively better out there, in which case please tell me, or it could be that our problem is novel and that's why we need this one. Then we come to computation. So we've got a proposal, we've got a method, we've got a way of calculating the posterior. This is all great. Now I actually have to do the numerics. I have to, by that I mean actually do some sums, not numerical analysis. I don't do that bit, sorry. We have to calculate the posterior distribution numerically because it's not analytic. Unfortunately, not only is it a complex multidimensional problem, the posterior is horrible. It's not just multidimensional, it is incredibly spiky and correlated. So you end up having a posterior that you're trying to estimate being massively small and pointed, but through time and distance and mass. So something close up, less time ago and smaller, looks almost identical to something further away, further back in time and bigger, given that the only data I've got is the sensor reading. So it's really correlated and really small in that multi-dimension, and we've got a sample across it. So we kind of, again, this is kind of the demonstration of what we do. We take things that look good from you guys, so a bit of SMC, a bit of SIR, and we sort of mash it together and try and get something that works. We then calculate the probability that it happens, put it all together and see if it works. And it does. It happily does. So we've got an example here of our source term estimator. You've got some orange dots there, which are sensor locations placed from our sensor placement tool. You've got some of them going red because they've seen something. And what the source term estimator does is takes an estimate, a sample of the posterior distribution. So it's saying this is where the release could have been given the information that I've had from my sensors, and it gives you kind of a probability distribution defined by the sample of the posterior that you've taken. You can then combine all that to do a hazard prediction, and here it's a bit blocky because of the spatial resolution of the prediction. Not the model's fault, it's just that we didn't run it enough for this example. Here in green is our simulation of what might have happened. Sorry, here in red is a simulation of what might have happened. Here in green is an assessment of where we think the hazard is. And it's kind of shaded because it's more likely in the darker green areas, the thicker green areas, if you like. So we've said it could be anywhere here, and it's fading out, and it does encompass this red square. Which leads us to another interesting problem in that I need to over-predict my uncertainty. If I under-predict my uncertainty, I am in trouble. If I under-predict that, people die. If I over-predict it, well, that's kind of bad, but not as bad. So there is a bias in what we want to do here. We don't want to under-predict that area. But it's a hard problem, and with some of the maths, we can get somewhere near it. So we're kind of happy, right? Why am I standing up in front of you? Well, then there's the next bit. Then we've got a hazard chain. Okay, so I've given you a hazard area, something's happening, but how does that affect people? Well, then we have things like dose calculations. I need to calculate, well, what's the effect? How do I calculate which bit's red and which bit's green and which bit's yellow? Well, that will depend on its effect on a person. So what's that person doing? Are they running up and down and inhaling a lot, or are they kind of asleep and not inhaling very much? Are they young? Are they old? What happens when they inhale that? How does that infectious dose react in their body, or in a chemical? How does that chemical react to them? So within that, there's dose response curves. They've all got lots of choices. So in here, that's just a very simple, and you'll get the slides, a very simple illustration of the kind of chains of models that we go through. So we're taking meteorology, something that we know is highly uncertain. We are then estimating a source term, which we know is uncertain because of all the input parameters that we can't know. We are then modelling the dispersion through the atmosphere using a probabilistic at best model. We're then figuring out where that went. We're making assumptions about how people react to that. We're modelling how they respond to that, how it's penetrating clothing, how it's going through the skin, whether they're inhaling it. If I just Monte Carlo'd it, by the end of that, I basically go, somewhere between 0 and 1, the end, which is not particularly helpful. That's why I'm here, because this really is the kind of the fundamental problem of uncertainty propagation, and I want to quantify it, I want to communicate it in order that a decision maker can make a risk assessment and a decision. So all of the things that we've talked about require model runs, and those model runs take time, and the more accurately I predict them, the longer the model runs take. So I, like you guys, think, well, I'm going to break this problem down into parts, and the most sensible thing that we might start to do is to look at emulating the dispersion model so that we can run it quicker, so that we can run it more time, so that we can get a better answer out of our source term estimator, out of our sense placement tool, out of our hazard chain. Because if I can run it more, then I get a better idea of what's going on. I can do my sensitivity analysis, I can do my parameter estimation. However, emulation, while possible, and I do mean emulation here, not surrogate, I am a Bayesian, I am doing emulation, and I use the word significant with caution always, but I do mean significant. There are significant challenges. The input space is massive. The output space is massive and functional. Met and terrain mean that every scenario is different. So if I release it in Cambridge, choose my words carefully, if something is released in Cambridge, it's very different to if something is released in Scotland or London or France, or so where the trees are, where the buildings are, exactly where the release was, what the Met's doing, what the Met's likely to do, is all different. So does that mean I have to build an emulator for every single possible release location in the world? Or can I have an emulator that works everywhere? That's an open question. So let's start at the beginning. Now we hit maths. We are going to, I apologise to all the applied mathematicians, I will change the talk when I get back. We are going to let xi be a vector of input values, not a spatial grid. We're going to let the vector s be the spatial grid. So there we go. Y is the vectorised output. I think we all agree that y is the output. Are we all happy with that one? No? No, we're not even happy with that one. Well, I define this and it's my talk. The first thing we need to do, because we want to get an emulator, is a little bit of dimension reduction. And there was a really good idea a little while ago by a group at Los Alamos led by Dave Higdon that said, well, you can fit a basis function to reduce the dimensionality of your problem, and that will allow you to fit an emulator. So how does that work? Well, you basically still have a linear model, but instead of just having your outputs, you now have your basis function in place of your x's, and that's a function of your x's. So then we have a set of basis functions, we have corresponding coefficients, which is a vector form. You can go through this and convince yourself, but then you need to choose a whole bunch more stuff, so I'm going to choose them all to be normal because that makes everything easy. We then end up with a slightly smaller covariance matrix. So the bit that Tony gave a really good talk this morning that told us how to do it, but the bit that wasn't in there is that generally when you're fitting a Gaussian process, you need to invert a matrix, which is why you said it's great in sort of 10 to 20 dimensions. Any bigger, it becomes a problem, and the reason is there's a really big matrix you've got to invert of a scale of the number of dimensions. So if you can reduce the number of dimensions, that's good. For all of the applied mathematicians out there, other ways of doing it might be ways to invert that matrix without making it any smaller. If there's cool ideas of doing that, then that would be an interesting research topic. So we've made it smaller with a basis function. The covariance matrix then can be sort of split up in two ways, because you can either say, oh, it's all independent, or, again, unfortunately, after I started this work, John Turigio came up with a really good way of separating out this covariance matrix to make it easier to invert, basically. And he would have saved me about 18 months' work if he'd done it 18 months earlier, but never mind. So we come up with, thankfully, oh please Tony, a Gaussian correlation function. This completes the specification of my model. We're going to assume some beta priors, and then we can get point prediction and the uncertainty around each point, and we can define an emulator. We can use this setup to model dispersion, because dispersion is highly multidimensional. So in our case, we are going to take an input as a two-dimensional vector. The sharp-eyed amongst you will realise that I've massively cut that down. The reason I've cut it down is even with the basis approximation, it still gets too big too fast to invert for things like spatial location. And that's because I cannot get a big enough training data set to allow my emulator to distinguish when my plumes can move about in space, because they drop off. There's huge areas of zeros. So if I just fix it, shift it, translate it, and then just change sort of the wind speed and mass, then the zeros remain in the same place, and I can run enough model runs to train an emulator. If I was to extend it to location, that would shift the whole area left and right, and then I would need more training runs, and as soon as I have that many training runs, my matrix inversion is too hard again. So can this be extended by you guys? Yes, please do. I would be very interested. The next thing is that dosage is output over a grid. It's obviously not output over a grid, it's output over a continuous space, but I have to discretize it. So I'm going to take a k by k grid. So what does it look like, and why am I worrying about it? Well, it looks a bit like, that's the contour plot of it. So we've got a release location here, it blows downwind, this gives you dosage, so it's already integrated over time. And middle bit's the highest area of dosage. If you look at a 3D plot, what happens is, at this point here, it drops off a cliff. And it has a massive point at the release location where the concentration is enormous. Now, I tried fitting all sorts of things to that shape, and that's on a log scale as well. The only thing I could get to fit was a thin plate spline, because it allowed for that massive change here, because everything here is nice and smooth. It's this bit that causes all sorts of issues. Thin plate splines work, so we tried a vanilla approach with the principal component emulator that Higdon came up with. Then we tried the same approach with a thin plate spline emulator, and then a bit later when Jean-T Rougier published his work and I realised that I didn't actually have to do the fully Bayesian approach, we instantaneously managed it with his separable emulator, and we obtained all of the information from it for a plug-in approach. So thin plate splines, again, a very good paper by Wood actually told me what I needed to do rather than me wading through figuring it out. So we chose the thin plate spline as a basis, we fitted it using a set of training runs, some of which were used to estimate our parameters, some of which were used to do assessment over our 8x8 grid. The separable emulator is trained using the same 40 runs, but then we have some other things that we need to estimate, and that's done using the 35 other model runs. So, how does it work? We have actual, we have the principal component emulator, which isn't quite as good. We have our fully Bayesian approach, we have our separable approach, easier to see here. So that's the singular value decomposition, the vanilla. That's the independent thin plate spline, so that's the fully Bayesian approach, and that's the separable one. It actually works really well, and the reason it works really well is that the thin plate spline is able to encapsulate the spatial structure of the dosage plume and basically take away from the emulator, from the Gaussian process, the spatial structure of the plume, which allows the Gaussian process just to fit the rest. So we were talking, I think, earlier about how do we find the mean function. Well, this allows us to sort of find the structure in that mean function, and it seems to work really well. It not only reduces the dimensionality, but allows the emulator to really find where it needs to be. Which is why this SVD doesn't work as well, because although it's minimised the dimensionality, it's allowed me to invert the matrix, it's not encapsulating that very specific spatial structure that I have. So that's great, but I still need to do the uncertainty quantification, and all I've done there is emulate a dosage. I still haven't emulated a concentration through time. I still haven't emulated across multiple locations. I've done that in one location. I still haven't done it across multiple MET parameters. I haven't taken it so far as to go through the chains. All I've done is a proof of principle. Can I use emulation to speed this up? The answer is yes. But now there needs to be some fairly substantial expansions to allow me to do it to the kind of things that I need to do it to. The other interesting thing is that's on an 8x8 grid, and when you have a dosage plot, so forgive me for skipping back, it's kind of, well, it's got this discontinuity, but other than that it's quite smooth. As soon as you start to worry about concentration through time over complex terrain, it stops being smooth and it stops having so much spatial structure, and the dimensionality increases exponentially, so it starts getting even harder. Unfortunately, it also means that the dispersion models are much slower to run in that case. And when the dispersion models are much slower to run, I can do much less with it. But I have a method that will encapsulate some uncertainty. So how then do I add in the rest of it? Well, I can start to use some of the things that we've talked about. I can start to use some Monte Carlo. I can start to chain emulators. How do I encapsulate the uncertainty in the real data? How do I propagate that through? How do I worry about the model discrepancy? How do I worry about the fact that the uncertainty explodes through here? Because actually meteorology is the most uncertain step and it's right at the beginning. How do I represent such an uncertain output in a way that will allow someone to make a decision? How do I communicate that to them? Now, okay, devil's advocate, and I've had people say this, I could just say I don't know. I could just say, actually, by the time I get to the end of that modelling chain, the uncertainty is so massive, I can't really say anything. And at the moment, mathematically, I guess you could say that's the case. But is it really? Is that really the case? Well, no, it's not the case, because if I was a commander on the ground being shot at, then I know an awful lot less than the scientist that knows, well, actually that sensor did go off there, and actually I've got an idea of where that wind was going, so I kind of have an idea of where it's going to go, and I kind of have an idea that if that's a biological agent, then that's going to have an effect on someone, and I kind of have an appreciation of what that effect might be and what I might need to do about it. And you know what, at the very least, run upwind or crosswind. That's a sensible piece of advice, right? Get out the way of the plume is a sensible piece of advice. The uncertainty about that might be high, in that, you know, I might not know exactly which way the wind is going, I might not know how fast it's going, but it's a sensible piece of advice. Even if I don't really know which way the wind is going, but you're on the ground, run upwind, run crosswind is a sensible piece of advice. It's not what's coming out of my mathematical model, but it's a sensible piece of advice. So, communication strategies. The hazard area is hugely uncertain, but you have got to give information in a concise and clear manner. The large uncertainties are unhelpful. It's got to be obvious what they should do with the information that you're giving them. Underestimation, as I've said, is bad, so we almost want to build in and I say this with caution, we want to build in a bias, because it is worse to underestimate than it is to overestimate. Spatial uncertainty is difficult to portray. We can't even calculate it properly yet, let alone draw it. That's the next step, maybe. But it doesn't mean we can't start trying. It doesn't mean that we can't start trying to make this a bit friendlier. So this is a hazy outline, but already it's giving a little bit more indication that I might not be sure about where that red area is. It's a very simple thing to do, but it just helps. Is it the best way of doing it? I don't know, but it just helps. There is a big new project looking at how we might portray this, so if you have any good ideas, if you're interested, watch this space. We should be running a workshop in April looking at how we might start to communicate these kind of things. It will draw in some of the epidemiological models from my colleagues at Public Health England as well, which is obviously the next stage on. If these things are contagious, it's not just the release we're worrying about, it's the spread then through the population. Flu is a good example of that. It spreads, you need to know who's in contact with who sneezed on who. Age structure matters with flu, for instance, because unfortunately small children slobber a lot more than grown-ups do, and if you have small children, you're far more likely to get the flu. Never mind, but I have small children, ended up with the flu. So that spread is really difficult to model and just adds in another level of complexity, but we need to worry about it. So, I must have talked massively fast, but I'm going to give you a time frame. I've already given you a complex problem, I think. At least it's hard for me. If anyone thinks it's easy, then come find me. This makes it even harder. So initial data will be received at a wide range of times post-event, depending on the scenario that you're in. If I've got a real-time sensor, then I will get data as soon as it's hit. If I have a sensor that requires a culture, for instance, that might be a couple of hours. If actually I'm in the scenario where there wasn't a sensor for some reason and I'm worrying about getting information from people presenting in a hospital because they're sick, we could be talking of the incubation time of the illness. That can be a couple of days. But as soon as something's happening, we need to start doing something about it. So initial responses are required within a few minutes. Hazard assessment is required within a few hours. So where's my risk is required within a couple of hours. So all of that source term estimation, all of that modelling, all of that dispersion model running, all of that prediction, all of that hazard assessment is within a few hours. And hopefully, you're going to have a supercomputer to do that on, great. But actually you might not have. So something that requires a supercomputer to run, not as good. Then analysis on alternative courses of action, right? What do I need to do? Who do I need to treat? Where do I get people out of the way? All of the questions from the policymakers are going to be coming in that 12 to 24 hour time frame. So all of your models that take a week to run, too slow. 12 to 24 hours, I need to have figured out the effect of potential courses of action and allowed analysis on the effect that they might have. So that's not just one or two of that full model run, that's potentially hundreds of that full model run. And I need to be able to communicate that to a decision maker in a clear and concise manner. Now, why did I put a time frame up? Because even here, where we have been talking about emulators and surrogates, the time scales that you've been talking on have been still days to weeks, I would say, and that's just too slow. However, I don't need it to be, I need it to be accurate, but I don't need to be super accurate in that 12 to 24 hours. I would prefer you to give me this is an area of risk with large uncertainty that I can do something with quickly, than wait a month for something that's very accurate. Because while it might be very accurate, it's a bit late. And by a bit late, I mean I can't treat people if, we're a month down the line. I needed to treat them a month ago. So give me something so that I can tell people, start treating them, know where they are. And I think that's really worth bearing in mind, because potentially each of those timescales will require a different type of mathematical analysis. I don't think that a full emulator is necessarily required up here. So what do I need? Because I'd like to do better than a wet finger in the air, and I think we can. I think we might be able to build an emulator that's giving us kind of numerical uncertainty here, but I'm going to have to be making sacrifices as to how much uncertainty is in there. I know that, but how much, and can I, and how do I extend it to the spatial structure that I think we will need. So in conclusion, hazard assessment is, in my opinion, not easy. But, as has been shown from the very complex talks that I've been given over the last couple of days, you guys are smart, right? So, let's figure it out, shall we? Multi-objective optimization across large multidimensional spaces is difficult, particularly when you have complex cost functions. I think some of the stuff we've been doing might help. Source inversion, we've got an inverse problem in there. That's hard. There's work in there that I think we could do to speed it up. Propagating the uncertainty, and note here I haven't said uncertainty quantification. I've just said propagate and estimate the uncertainty. That's still hard and still needs to be done. There are tools under development, and there are tools that are there and they're working. Here, propagation and quantification of uncertainty through the hazard chain is obviously an open problem. If you can actually quantify the uncertainty and encapsulate everything, because I need model discrepancy, I can't ignore it, I need parameter uncertainty because I can't ignore it, then that's great. Let's work towards that. But always remember that you've got to then communicate that, and it's not the uncertainty, it's the risk that I'm going to be worrying about. I too have a selection of references. You can look at them in your own time, but I will leave it there and ask any questions.
Questions?
Stunned into
You
silence.
can take a few minutes to think. Some questions? Yes.
In your final section there, where you referred to the aversion of decision makers to high uncertainty, there's an implication there that the communicator, such as yourself, has implicitly already made the decision because they have to formulate their recommendation in a definitive kind of way. Is that correct?
Yes, it is a balancing act. So the more I distill the information that I have in a way that makes it very easy to use, the more of my judgment I'm adding into that to refine it. That is a two-way process. So the way that we do that at the moment is that we build up a working relationship with the decision makers. So for instance, we will expose them to a wide variety of potential outputs and let them define and work with us to get something that they understand. I don't think we make the decision for them, but we do refine the information that we get in a way that will help them make a decision. But yes, we will always be abstracting the problem, and in that sense we kind of know the answer to some extent. Does that make sense?
Well,
you no doubt have a bunch of models appropriate for all sorts of different situations, but you'll be able to classify situations where you're going to use this kind of a model, and probably depending on the speed of reaction, and you probably use pretty much the same speed of reaction for the class of models, you're going to choose a model of particular level of sophistication. And that may not be the most complex model available because you can't run it in the time. But the thing about the quicker model is that not only can you run it then, but you can also have run it many times before, built your emulator, validated your emulator, learned all about how it performs, and even have some observational data with which to say just how well it conforms to reality. So are you engaged in those sorts of processes to prepare yourselves?
Yes, is the short answer, and somewhat is the longer answer. So yes, we have validation exercises. We work a lot with the US, and they run trials with inert gas generally and inert aerosols, and they will actually take sensor readings, and we will have a dispersion model, the quick running ones, the slow running ones, and we'll validate those models against them. We will also use that kind of data to validate basic emulators. However, at the moment, it's an open problem, particularly. So the dispersion models, yes, we do, but for an emulator, it's an open problem as to whether we need to train an emulator for each possible spatial location because of the way the models interact with the terrain. So even the simple dispersion models, when hit with a hill, for instance, what you'll get is puff splitting, so they all go around the hill. It takes time in the order of minutes, but you need that because it's such a big effect. Whereas if I'm running an emulator, it's very difficult to train it a priori what to do about hills in a random, because I don't know where they're going to be. So I don't know how to train an emulator in that way yet. So I guess yes, the answer is yes, we're doing it with the dispersion models, but not yet with the surrogates or emulators.
Do you have sorry, just a quick follow up on that. You know where your forces are, where the establishments are. Okay, so you know in advance to some extent where these things are likely to be. So can you not do something based on that? I know they move around, but they're not that fast.
Yes, we can. So if we have an established base, we will assume that we can pre-run. We will pre-run a library of dispersion models. We won't pre-emulate for the reasons I've stated, but we will pre-run dispersion models, yes. However, that works really well in the deployed sense because I know where my base is. It would be a very big library that covered all of the UK, for instance. So you might pre-run for, and we do pre-run for places, but it would be for a worldwide pre-run, that would be really hard.
It was the same question actually at this point, that if you know something, if you know an event is going to take place, like a royal wedding or something, for example, and you can think about
yes.
maybe doing these things around Windsor. But I don't understand your second point.
You know I'm not going to comment on that, right?
But I don't quite understand your second point about why, for example, if you know a particular area, you're going to have to worry about why you can't do the emulation in advance as well, because you know the terrain in that case.
Because at the moment, the emulator isn't run. I can't train an emulator if I don't know where the location of the release
But I know where Windsor is. You know with the release.
Yeah, because where the release is, if I hit a hill, so if I'm standing
Can the release parameters be input into the emulator? Your inputs into the model?
No, because if the release parameters are input into the emulator, then the dimensionality of the input space for the emulator is such that you can't run enough training runs to allow it to distinguish. So when we added in the location, what you ended up with was you can get to about 80 training runs before the matrix inversion falls over, and 80 training runs was not enough to allow the emulator to see the difference and see the structure in a plume that looks here to one that looks here, because there's too many zeros. I think if I could have a couple of hundred of simulation runs to train it, I could start to have X, Y as an input into my emulator, but the inversion breaks, even with a basis.
Can't you use something like a highly reduced order model, an ordinary differential equation instead of PDEs, as the emulator itself? You can run that a bunch of times. It can actually learn something about terrain, and now in your quick scenario, you can actually just run the ODEs, and you can actually do that quickly enough.
Very possibly. That might be a good thing to look at.
We've done something like this for flows over real terrain, not in the atmosphere, but on the terrain, and it serves a purpose that's quite useful.
Okay.
Just one question.
I'm sorry I came in late, but I'm starting to get what you're doing. And I was just wondering, there's several companies that I've talked to, and the Met Office as well, that are doing very, very similar things. DNV GL does risk assessment of plants. The National Physics Laboratory does very similar things. Met Office is very interested in source detection of. And so I think I was just wondering whether you collaborate or look at what they are doing, because I think it's kind of would be good to to join.
Yes, so there are a number of government groups that all work together. We all collaborate, and then we each have responsibility for specific scenarios. So, for instance, the dispersion models that we would run look at things that don't puncture the boundary layer, specifically look at chemical and biological releases below the boundary layer. If it was something like a radiological or a nuke, then that would be AWE. If it was something like the Buncefield disaster that punched the boundary layer and was pollution, that would be the Met Office.
I'm more talking about the methodology than about the actual scenarios. I'm just saying,
So yes, the
if you join
methodology,
efforts in getting the methods
yes,
together.
the methods we work together on. Yeah.
Yes.
Me?
Yes.
Yeah, okay. Possibly a somewhat minor technical point, but earlier in the talk when you were talking about dispersion modeling, you referred to the use of a Gaussian distribution. And I was wondering what that referred to. Does it refer to the position, the uncertainty in the position of the emission point, or does it refer to the density at the deposit point?
It refers, so a Gaussian dispersion model basically assumes that it models the dispersion as a series of what we will call puffs, which are instantaneous releases, if you like, and that puff, which contains the concentration over space, is modelled as a two-dimensional Gaussian distribution that then moves through time. So
it's the shape of the puff,
yeah,
not the density, not the concentration.
It is the shape of the puff, but the way it works out, the concentration is Gaussian, but deposition isn't, I think, is the way around it goes.
Usually in atmospheric pollution problems, the density of the pollutant is usually best modelled by something like a log normal distribution.
Yeah, so we tend to, so the concentration at a point we tend to model as a clipped Gaussian distribution, which is different to a Gaussian clipped, but yes, so it is best modelled by that, you're right.
I think unless anybody's got a question they want to ask.
Well, just one more. The concept of hazard area, so you feel that the decision makers like you need to overestimate the extent of the hazard area a little bit just to avoid the errors in the wrong direction. But to define the hazard area, also some choices have to be made, especially if you have these Gaussian assumptions where there's no hard bound at any point. So is it the case that you have to make those choices on how the hazard area is defined, or do the decision makers somehow guide you towards a certain criterion for what falls within the hazard area or not?
So it is a mixture of the two. We talk to the decision makers and we try to discuss with them the levels of risk that they will worry about, but there's a trade-off. So think about your hazard area as an area where you might treat someone. Giving someone a treatment has an inherent risk in it. So if I was to give someone antibiotics, for instance, there would be adverse reactions to the antibiotics. If I gave it to a huge number of people, there would be a lot of adverse reactions. So generally what we do, and what we've agreed with the decision makers, is that we will model a hazard area out to the point at which the probability of them getting infected equals the probability that they will have an adverse reaction, if you see what I mean. So it's kind of us deciding where those probabilities lie by doing our analysis, but it's with discussion with the decision makers that that's where we give them the boundaries. And then generally the other boundaries are defined by the decision makers in that they will say, well, I can do something effective with this many people initially. So we will give the first hazard area is, well, this is the chunk of people that you need to deal with now, then these are the ones in the next level of risk, so you might be able to wait till the next time round. So that's a two-way conversation, because if I say, right, your hazard area is this big and there's this many people here and they can't deal with that, then that's no good. So what we have to do is work together to say, right, how many people can you deal with? These are of the highest risk and they lie there. Now that's, because you will have more time, the less risk people are under, the more time you'll have to do something about it. So that's generally, it's not about necessarily actual probability levels, it's more about the areas that you know you can do something about in a sensible time frame.
If those are the considerations, then I would say that it's the decision maker who has to interpret things correctly, and there shouldn't be no need for you to overestimate anything.
You fell into the trap. That we said it sounded like a trap.
So, right, let's clarify. When I say overestimate, overestimating is still bad, because I could say, right, well, all of London, say. But then I've got an issue that I'm treating people that were never anywhere near it, and you've got the adverse reaction problem. So overestimating is still bad. The point I would make is that if you don't know, don't underestimate, because it is much worse not to treat someone than it is to treat them. So yes, if you have worked very carefully and all of your models are good and all of your parameter uncertainties are known, then fine. I guess the point is, if I don't really know where that parameter uncertainty lies, and I might be able to pull in my uncertainty a bit, I think, because one expert says I might be able to, but the other one says not, I'm always going to err on the one that's more cautious until I know more certain. Does that make sense?
Okay, I think our future is in very safe hands.